Here's what we're going to do today. Yesterday, we went through pretty much all of the ideas in 4.3. We talked about how we can use the derivative because the derivative keeps track of slope to indicate where a graph is increasing or decreasing. So if the first derivative is positive on that portion of the graph or on that interval, that's going to be increasing. If the first derivative is negative, that's going to be decreasing. And we use those patterns to figure out where maxes and mins are. So if I've got a first derivative that's positive, then zero, then decreasing, it increases, negative, and so it increases into that point and decreases afterward. That's going to produce a max. Whether I've got a derivative of zero or whether I've got a point that where the derivative doesn't exist, that pattern is still going to produce that type of peak. So increase into this point, decrease after that point, that's going to be a max. In either case, similar argument for a min. It's just that we'd have a negative derivative on this side, a positive derivative on this side. So it would decrease into that point and then increase after. So that would produce a minimum. And we talked about the first derivative test, which is exactly what I've explained there. So if the derivative changes from positive to negative, that's going to produce a maximum. If it changes from negative to positive, that's going to produce a minimum. And if it doesn't change on either side of a critical value, then it doesn't produce an extreme value at all. So if it can increase into this point right here and then increase afterward, we don't have an extreme value. Same thing if we decrease to there, have a cusp or a corner or something like that, and then decrease afterward. Okay. We also talked about how we can find extreme values at endpoints just based on what the derivative was leading into that endpoint. We introduced the concept of a sign line. A sign line is a nice way to keep track of the sign of the derivative, because if we keep track of the sign of the derivative, whether it's positive or negative, that's going to tell us where it's increasing and where it's decreasing. So we did work like this, okay? Kept track of the sign of the first derivative, and that told us what the function was doing, whether it was increasing, decreasing, or level. We went through and did several problems, including one that had a cusp. And then we started talking about concavity. And concavity is like the curvature, which way it's cupped. So this portion of the graph is cupped downward. This is cupped upward. Okay, so we use the word concavity to describe that. And we went through several different definitions or descriptions of what concavity means or how you could figure it out. And by far the easiest way to describe it is using the second derivative. If the second derivative is positive, then it's concave up. The original function is concave up. If the second derivative is negative, then the original function is concave down. Concavity isn't quite as useful as increasing and decreasing for drawing sketches, but it does have some interesting applications, particularly in physics and astronomy and stuff like that. So keep those things in mind. We are going to show one other use for it that does come in handy occasionally for a specific type of question. We did example 7 where it says, find the first and second derivative and use a sign line to graph the general shape and find the extreme values. So we found the first and second derivative. We made our sign line, and you'll notice we were keeping track of information about the first derivative here, information about the second derivative here, and then kind of in the center is where we put it all together. We showed that it was decreasing, leveling off, then increasing, leveling off, and decreasing. If it goes from being cupped upward to cupped downward, we've got a point of inflection there. And we can see that because the second derivative changes sign. It was positive on this side of 1/2 and negative on this side of 1/2. So this point right here is going to be a point of inflection. I left you with, okay, we know there's a minimum at -2. What's the value? We know there's a maximum at +3. What's the value? And we want to find the point of inflection, okay? So I'm hoping somebody actually did that. Can somebody tell me what the minimum value is here? -63? We'll go with -39 since we've got 2 of those. Somebody might want to double check that on the calculator. If you, pardon me, if you plug in a 3, what do you get? 86, okay? Big values. I mean, think about where these would be on a graph. These would be nowhere near a standard window. These would be way up above the top of the screen and the bottom of the screen. And then what happens if you plug in a 1/2? 23.5. Holy cow. So even the point of inflection, I'm going to write it as 47/2. Even the point of inflection wouldn't be on the standard window if we were to graph this on a calculator. And think about how hard it would be to see and guess where it changes concavity. So we've got a graph that's cupped upward and cupped downward. You can tell roughly where the point of inflection would be. You could tell it changes concavity, but finding out exactly where, you have to have the second derivative. You're not going to be able to look at it and say, oh, it's going to be at 1/2. Okay? Doesn't work that way. All right. Any questions? Peter, did you confirm? Okay. Well, we'll blame it on your calculator either way. All right. Okay. So let's take a look at this thing called the second derivative test. And if we notice on this graph right here where we have a minimum, the first derivative is 0 right here, and it's concave up. If it's cupped upward and the first derivative is 0, that's got to be a minimum. And right here, it's concave down, so it's cupped downward, and the first derivative is 0. So we could use this idea to cover something called the second derivative test, and here's how the second derivative test works. I mean, if we have to sketch the whole thing, you might as well sketch the whole thing, and this test isn't very useful. But if all you have to do is say, where are the extreme values, and are they maxes or mins, and what are they, and stuff like that. If you don't want to sketch the entire thing, then what we could do is this. We could just say, if you find where the first derivative equals 0, and you figure out that it's concave, let's see, if the second derivative is greater than 0, that means the second derivative would be positive. That means it's concave up. If the first derivative is 0 and concave up, then you're going to have a minimum. That's this situation right here. Cupped upward, flattens off for just a second, levels off for a second. That means we know we're going to have a min right there. Okay? If the first derivative is 0, so the function flattens off, levels off for just a second, and the second derivative is less than 0, or in other words, it's negative, it's going to be concave down, that's going to have a maximum. That's going to be this situation right here. Okay? So all we want to do on this one right here is just use the second derivative test to kind of confirm what the extreme values are. Okay, we already know that the derivative at -2 is equal to 0. We know that the derivative at +3 is equal to 0. Let's check and see what the second derivative is at each one of those points. So the second derivative is this guy right here, which I'm going to write like this. -12 and then 2, excuse me, that's a -2, isn't it? -2 minus 1/2. What do we really care about here? We only care about the sign. We don't really care, gosh, we could put those together. That would be -5/2 times 12, so that would be -60/2, so it would be like -30, I think. Or, excuse me, +30, because this is going to be negative times negative. We care that it's positive. So that means it's concave up and levels off. We're going to have a minimum. We know we've got a minimum there. And if I check the second derivative at 3, this is -12, and this is going to be 3 minus 1/2. So this is negative, and this is positive. I know I've got a negative. It's going to be concave down. That's going to force us to have a max. Any questions there? So you can use the sign of the second derivative at the location of a critical value for the first derivative, where the first derivative doesn't exist or where it equals 0, to figure out whether or not you've got a max or a min. Let's think about that, though, for just a second. If the first derivative didn't exist at a particular point, would the second derivative suddenly exist there? Nope. Okay? And that's why this test just involves where the first derivative equals 0. Okay? Any questions there? Okay. So this next page, there's kind of a summary of the ideas that we've gone over. So this first little picture just says, if f is differentiable on an interval, then we get a nice smooth curve. So if it's differentiable, it's got a derivative everywhere. Okay, we've got a nice smooth curve, nice smooth connected curve. If the derivative is positive, the function's increasing. If the derivative is negative, the function's decreasing. If the derivative changes sign, then we've got either a max or we've got a min. So if it goes from being positive to negative or negative to positive, we've got an extreme value there. This right here says if the first derivative is 0 and the second derivative is less than 0, concave down, this is another depiction of the second derivative test. Same thing here for a minimum. Okay. If the second derivative is greater than 0, cupped upward, concave up. Could be increasing, could be decreasing. Okay. If the second derivative is negative, concave down. Could be increasing, could be decreasing. They're both cupped downward. Okay. And if the second derivative changes sign at a particular point, it's going to go from concave up to concave down. Then we've got a point of inflection there. But it's got to be continuous and it's got to change signs at that location. So this picture right here kind of describes pretty much everything we could come across. And really what we're after here is, again, like I said yesterday, I realize you've got nice calculators that will graph most of this stuff for you. Okay, that's not the point. The point is we can use calculus to describe a lot of the details on the graph that you can see on a calculator. Okay, and we can also use it to precisely locate things that a calculator would have a hard time displaying or your eye wouldn't catch. Okay, that's all we're after. Okay, so we have example 8, A and B, and number 41 and number 46. So we've got about 40 minutes and 4 problems to do. Okay? Now, some of these would be fair game for the test. Some probably a little bit too difficult, but let's see what we can do here. So let's pay attention to the instructions. On example 8, it says, find the intervals on which the following functions are increasing or decreasing. Then use your calculator if necessary to graph the function and its derivative on the same set of axes to verify your work. It doesn't say sketch the graph. It just says find the intervals where it's increasing or decreasing. Okay? So let's do that. All we need for that is the first derivative. And for the first derivative on this, we're going to need to use the product rule. Okay? So I'm going to take the first times the derivative of the second plus the second times the derivative of the first. Just like before, we're normally going to be better off if we write this in kind of a factored form, simplify this to a reasonable degree so we can use it again. This is going to be e to the x and then x plus 1. The places where this can change from increasing to decreasing, and by the way, this is a continuous function, isn't it? Okay, we don't have any domain issues or anything weird like that. No even roots, no logarithms, and no division or anything. Okay. So we want to know where this equals 0 or where this does not exist. Well, it equals 0 at x equals -1. And is there anywhere where it doesn't exist? Nope, not a single place. So if the instructions are just to identify where this is increasing or decreasing, this is pretty simple. Okay, and then to make sure we're clear on this, when I write numbers up here on the sign line, those are values of x. So the only number that I'm going to put on my sign line here is -1. And the reason I put it there is because the derivative is 0. So don't confuse the values that I'm putting down here, because the derivative is 0, with the location of where that happens. These are x coordinates here. Okay, I'm figuring out where stuff happens. Good? Okay. Now, in this nice factored form, what can you tell me about e to the x as far as its sign? Always positive. It's an exponential. It's always going to be positive. So I'm going to have a positive times some number that I get when I plug in a value that's on the left side of -1. So pick anything you want less than -1. Pick -400 if you want. When you plug it in here, you're going to get a negative. So I have a positive times a negative. So that means the sign of the first derivative is negative there. If I pick any number I want that's greater than -1, 0 is very easy. Plug it in here. We already established the fact that that first factor is always going to be positive. If I plug in a number bigger than -1, that second factor is also going to be positive. So I get this. So the question here is, Where is this increasing and where is this decreasing? That's it. So it's increasing on 0 to, or sorry, get the right thing here, -1 to infinity. If you wanted to, you could put a square bracket around the -1. Okay, even mathematicians argue about that. It doesn't really matter because remember, increasing and decreasing are defined on intervals, so you can't really say it's increasing or decreasing at one single point. Okay, most people like the round brackets here though, and then pardon me, then it's going to be decreasing from -infinity to -1. So we're looking for a graph that does this. Goes down, levels off, and then goes up. And this point right here would be -1 comma something, and we could figure out what it is by plugging into the original function right here. If I plug in a -1, I get -1 and then e to the -1. -1 over e, right? So that means the coordinate axes would be over here somewhere. It didn't ask us to sketch it, but when we graph this on the calculator, we're expecting to see something like this. So let's grab the calculator, and then let's type in the original function. And it also says graph the function and its derivative on the same set of axes. So let me clear this off. I'm going to type in x and then e to the x. Okay, I'm going to type in its derivative also. That is e to the x. Close the parentheses, and then we found that it was x plus 1. Close the parentheses. Okay, I'm going to come back here and I'm going to turn this off. And these are pretty small numbers, so that I can get a decent look at this, I'm going to hit zoom 4. I'm going to graph this in the decimal window. And that looks pretty good. Decreases here. Hits this point right here that's about -1/3, and that looks about right, and then it increases after. Okay, then I'm going to come back here and I'm going to turn this on. So here comes the derivative. Okay, now I can't see that very well, so I'm going to zoom in. I'm going to hit 2 and hit enter. Really zoomed in there. Okay, and I'm going to slide this over just a bit. So I'm going to take this and I'm going to go -2. There's the original graph, and there's its derivative. Okay, notice the derivative is negative right here, so the original function is decreasing. It's 0 right here. So the original function has leveled off for just a second. Derivative is positive, so from here forward it's always increasing. So there's our negative derivative, our 0 for derivative, and our positive derivative. So this is kind of a graphical representation of what our sine line showed us. Any questions there? Okay, let's take a look at the next one. Same instructions for this one. All we want to do is identify the intervals of increase or decrease. So we've got a restricted domain. We're only going to go from 0 to 2 pi. And here's this darn trig stuff coming back at us. So again, I've got to find the derivative. So we're going to find y prime. That's going to be 1. This is going to be, well, let's see. Derivative of cosine of x is negative sine of x. So that's negative radical 2 sine of x. Okay, this function right here is continuous on this interval. Okay, nothing weird happens there. And this derivative exists everywhere on that interval. Okay, this is a sine graph that's been vertically stretched just a little bit, flipped upside down. Okay, instead of starting at 0 and going up, it's going to start at 0 and go down. And then we slide it up 1 unit. Okay, we'd normally write it as negative radical 2 sine of x, and then plus 1. That bumps the graph up 1, the negative flips it upside down, and the radical 2 changes the amplitude. Good? Okay, so what do we want from this? We want to know where that equals 0 or where it does not exist. We already covered this, that it exists everywhere. So let's go ahead and solve this. I'm going to move the 1 to the other side, so this is going to be negative radical 2 sine of x equals -1. Then I'm going to divide both sides by negative radical 2. So what I've got here is this trig equation. Which might look a little better if I wrote this. It doesn't matter. If you want to rationalize the denominator, go right ahead. That should be something that you recognize. If you don't, you can always do this. This is the opposite side, and this right here is the hypotenuse. So the opposite is 1, and the hypotenuse is radical 2. If you wanted to take the time to go through the Pythagorean theorem, guess what this side is? It's 1 also. This is a 45, 45, 90, but remember, we're working in radians. So this answer right here is going to be pi fourths. If you took the sine inverse of both sides here, if you did the sine inverse of radical 2 over 2 or 1 over radical 2, your calculator would tell you 45 degrees or some ugly decimal if you were in radians. Okay? Question? Very good. Very good. Your calculator will give you this answer, but remember, we want all the places where the sine has a ratio of radical 2 over 2. Happens over here also, because this side would be 1 and this would be radical 2. We really don't care about what the adjacent side is, what the x-coordinate would be there. What we care about is these two sides right here, the opposite and the hypotenuse. So this would be 3 pi fourths. Same reference angle of pi fourths. That angle would be 3 pi fourths. So I've got two places where the derivative equals 0. Two places where the derivative equals 0. So on the sine line, and again, these are x's, I'm going to put pi fourths right here. I'm going to put 3 pi fourths right here. And 0 and 2 pi are there because they're endpoints. We don't really care about that because it doesn't say find maxes or mins. It just says identify intervals of increase or decrease. Okay? So the reason these are on there is because the derivative is 0 here and it's 0 here. So all I need to do is pick a number here, here, and here, and figure out what the sign of the derivative is. Okay, and there are several different ways to do that. Okay, let's take a look at this right here. So y prime is equal to 1 minus radical 2 sine of x. What's that? Yeah, they'll come back to get you. Okay, I'm gonna graph what this must look like. This was moved up to 1, and sine normally starts on the center line and goes up, but the negative makes it go down. So it's going to look something like this. And this is 0, and this is 2 pi. I think this is the easiest way if you know how to graph these. Okay, I mean, you should. We just changed the amplitude, flipped it upside down, and slid it up 1. Okay, guess where this hits 0? Well, we just found those points, didn't we? Hits at pi fourths and 3 pi fourths. So here and here, the derivative is positive. It's above the x-axis. So we're positive here and positive here. What is it in between that negative pi fourths and 3 pi fourths? Negative. Now, if you need to pick an angle, if you want to plug in, 22 degrees or something like that, if you want to plug in pi eighths into your calculator and have it give you an answer, it will give you a positive answer. Because if you think about this, until we hit, this is 1 minus something, and sine of 0 is a pretty small number. In fact, gosh, that would be a good number to plug in. Isn't 0 on this side of pi fourths? Yeah, and what's the sign of 0? 0. So this is 1 minus 0. That's positive. So it's positive in here. Okay? An easy number to plug in here would be pi halves. Plug in pi halves. This is going to end up being 1 minus radical 2 times 1. So that would be 1 minus radical 2. That would be a negative 0.4-ish. Okay? You'd get a negative value here, and then plug in any number over here, you're going to end up with a positive. Okay? So this is not a difficult calculus question. This is a hard trig question for some people. Finding the derivative and setting it equal to 0, that's the easy part. Okay? Derivatives are easy now. Setting things equal to 0, well, no duh, anybody can do that. It's what comes after that that causes people trouble. Okay, now, once I figure this out, what do I know about the original function? Increasing, level, decreasing, level, increasing, right? So, where is this increasing? From 0 to pi fourths, and then again starting at 3 pi fourths and going to 2 pi. Whoops. I guess we could use square brackets on those if we had to. And where is this decreasing? Only between those 2 points right there, so only between pi fourths and 3 pi fourths. Okay? And again, these are not points. Please don't mistake those for points. These are intervals on the x-axis where it's increasing or decreasing. Any questions? Yeah. Because they're endpoints. Yeah. Again, increasing or decreasing, they're described on intervals. Okay, so whether you do a square bracket or round bracket isn't that big a deal. You could argue with somebody if you wanted. Yeah. Would the point of inflection for this one be pi comma 1? Let's see. So Juan's question is, if we were to wonder about points of inflection on this one right here, it would have to change concavity. We'd have to think about where is the first derivative changing from increasing to decreasing. So if this is the derivative, okay, think about the derivative. Okay, how is it changing? Or in other words, how is the derivative of the derivative changing? Okay, this is, so let's think about it this way. This is negative, 0, and then positive. And then it's going to change from being positive, smaller positive, 0, and then negative. So yeah, about right there. I think so. You could confirm that by finding the second derivative, right? And you'd have a, what would you have? You'd have a negative, no, you'd have a negative cosine. Yep. Okay. Any questions? Okay. All right. So the last two problems, these are, I copied these out of the textbook, and here are the instructions. So let's just follow these through. I would say these are, this one's not too bad. The next one, I mean, to start off with, these are pretty tough problems. This is why I want to show you these. But with some practice, you should be able to do stuff like this. I'll try and pick something for the test that's kind of mild, maybe not quite this difficult, but the ideas on these two problems are very important, especially the algebra skills that we're going to go over. Because again, it's usually the algebra and the trigonometry that people struggle with when they're doing calculus. Finding the derivatives on these is going to be pretty easy. So let's take a look at this one. It says find intervals of increase or decrease, so just like the last problem. Find the local and maximum and minimum values, so we'd actually have to find the x value and the y value there. Intervals of concavity and inflection points, and then we want to sketch the graph. Okay, so let's take a look at this. If that's C, the first thing I'm going to want to do on this one is let's find C prime. Now, I really don't want to use the product rule on this, so let's take this and rewrite this algebraically. Distribute through. This is going to be x to the 4/3 plus 4x to the 1/3. The advantage I have now is this is now just a couple of power functions. So I can find the derivative of each one separately using the power rule and then combine the results. So this is going to be 4/3 x to the negative, or excuse me, the positive 1/3 if I reduce that by 1. And this is going to be 4x to the negative 4/3 x to the negative 2/3. Everybody with me there? That is not a very friendly format. So we're going to take this and we're going to change this. So some little known factoring techniques, some that would make this a little bit easier. I'm going to take out the 4/3. Everybody sees those have a 4/3 in common, right? Well, they've also got some sort of cube root in them. They've got a 1/3 power in each one of them. So here's what we're going to do. Okay, I'm going to take out the smallest of the two of these, or in other words, the most negative one. So I'm going to divide this one by 4/3 x to the negative 2/3, and I'm going to divide this one by 4/3 x to the negative 2/3. Factoring out is dividing out. I'm literally showing that I'm dividing those out. So I'm taking out a 4/3 x to the negative 2/3. What's left of this one? I'll tell you what, we'll do the easy one first. Look at this guy right here. What's left of this term if I take out 4/3 x to the negative 2/3? A 1. What's that? It is x. Look, the 4/3 cancel. If I move this up into the numerator, it would be x to the 1/3 times x to the 2/3. That would be x to the 3/3. So I've got an x plus a 1. This is a more friendly format. Probably the best format would be this. Let's do 4/3, and let's put this down in the denominator. This is going to be the cube root of x squared, and then I've got an x plus 1 up here. Okay. As far as actually using the derivative, that's probably the easiest format. Okay, can I erase this work here? That idea is going to come up again, so keep that in mind. So this is right, but that's probably the most useful. With me? Okay. So what do we want from this? When it equals 0 and when it doesn't exist. When does it equal 0? At -1. And when does it not exist? At 0. So here's my sign line. Remember, these are x's, and I'm keeping track of the derivative. The reason I'm putting these numbers on the sign line is, so I'm going to put a -1 on here, and I'm going to put a 0 on here. And the reason the -1 is on here is because the derivative doesn't exist. And the reason the 0 is on here is because, sorry, other way around. Because the derivative equals 0, and here it doesn't exist. Okay? So I was writing those down backwards. Got it right, didn't I? Okay. Any questions so far? Okay. Let's answer this first question right here. Let's figure out the intervals of increase and decrease. Okay? Because I'm hoping this will be pretty easy. Take a good look at this format right here. Okay, now, that's a 4, a positive 4. That's a 3, a positive 3. What can you tell me about this right here? Always positive, because whatever you plug in, it's going to get squared, it's going to be positive. Okay? So that means the sign of the first derivative is completely determined by this guy right here, just by the x plus 1. So plug in a negative number that's less than -1. Plug in a -2. What's the value of this, or what's the sign of this? Negative. Okay? So we're negative here. What if I plug in any other number that's bigger than -1? It's going to be positive. Okay, now, let's stop and think about this for just a second. With this information, clearly we can write down where it's increasing and decreasing, okay? So the original function must be decreasing. It levels off for a second, then it increases. Not quite sure what happens here, but then it increases after that. So I can write down the intervals of increasing and decreasing. But what does the function do there? So let's think about this for a second. The derivative doesn't exist. That means it's either a point of discontinuity. Does that have any domain issues? No. So it's not a point of discontinuity, so we can cross that off. That narrows it down to one of two things that we've typically seen in these. It's either got a cusp or a corner, or it's got a vertical tangent. Well, let's stop and think about how those cusps and corners showed up. We had like a derivative that was decreasing, and then a function that was decreasing, and then a function that was increasing, or vice versa. Is that what happens here? No. What happens is it decreases, it levels off, it increases, does something we're not quite sure of, but it increases after. What do you think we have there? Vertical tangent. Make sense? Okay. So can we say where it's increasing and decreasing? Increasing decreasing? Let's at least answer that. So it's going to be increasing. Well, this is pretty easy. It's increasing from -1 forward. And it's decreasing from -infinity to -1. Good there? Yeah. You can, because it will hit that vertical tangent at just one particular point. So it's going to do something like this. It's going to increase, go like that, and like that. It's still increasing. Like from this point to this point, it's still increasing over that interval. So yes, you can say that. Yeah, or you could think of it this way. You can't get much more increasing than straight up and down. Okay? You're really going up at that point. Okay? Any questions there? Okay. Max or mins? Okay. This is a min. Not only a min, we could be even more specific. Absolute min at -1, comma, and then we could plug that in. So if I plugged in a -1, let's take a look here. Okay, I'm going to plug it into this. I get a 1, don't I? Cube root of -1 raised to the 4th power, that's going to be a +1. What's the cube root of -1? -1. So this is 1 minus 4, so that's going to be -3. So we've got a point on the graph. We could kind of anchor this graph down. We know that this point right here is at -1, -3, so just drew some axes in there. Kind of a rough sketch, just to start with. Any questions? Okay. If there aren't any questions, then I'd say you're doing really well. Okay, because this is kind of a weird function. Some ugly exponents. Derivatives, not bad. Factoring, bit of a pain in the butt. Okay? Now, does this look like we're going to have some points of inflection? Pretty hard to tell. Okay? So let's go ahead and find out if we have any points of inflection. And for that, we need to find the second derivative. So I'm going to change colors now. I want to find the second derivative. And oddly enough, the one that was most useful algebraically, we'd have to use the quotient rule to find the derivative for. Product rule here. But what can I use here to find the second derivative? Just the power rule, right? So let's go ahead and do that. This is going to be 4/9 x to the -2/3. And check me here, make sure I don't make any silly mistakes. This is going to be -8/9 x to the -5/3. How are we doing there? Okay. So we're going to take out the smallest exponent, the most negative exponent. And I've got a common factor for both of these of 4/9. Okay, so I'm going to show the work here. I'm going to divide by 4/9 x to the -5/3, 4/9 x to the -5/3. So what I'm pulling out is 4/9 x to the -5/3. And I'm going to write down what's left. Okay, take a look at this one. The x to the 5/3 cancel. What's a -8/9 divided by 4/9? -2. Is that okay? 4/9 and 4/9, those cancel. If I move this up in the numerator, I'd be adding 5/3. So that's going to give me 3/3, which is 1x. Okay? So how cool is that? I'm going to write this down below here so I've got some room to show the rest of that work. Okay, and I'm going to erase this stuff also. That's the right derivative. Not a very useful format. This is a little bit better. Probably the most useful format, though, would be 4x minus 2, and the 9 on the bottom, and then this is going to be the cube root of x to the 5th. Okay? As far as using the second derivative, that's probably the most useful, right? Where does it equal 0? And where does it not exist? This shouldn't be any surprise. It doesn't exist at 0, right? And where does it equal 0? At x equals positive 2. So C double prime. Let's see, I'm going to put a positive 2 on here, and the reason that's there is because the second derivative equals 0. And then we're going to take a good look. So if I plug in anything over here, I know the derivative doesn't exist here. Well, maybe we should check here. Let's check positive 1. What happens here if I plug in a positive 1? That's positive and that's positive, so I really don't have to worry about that. This would be negative, and this would be positive. So it's going to be negative here, right? Doesn't exist there. What about over here? Pick any point you want. Take a look at the sketch that we've drawn, this rough sketch. It better turn out to be positive. Let's plug in a negative 1. If I plug in a negative 1, this is negative. This is also negative. So I've got a negative over a negative. That's going to be positive. Okay. And what happens if I plug in a number bigger than 2? Positive here, positive here. So this is going to be positive. Good there? Okay. So let's see. Concave up here. What about here? Between 0 and 2? Didn't we get negative? Let's double check that. Plug in a 1. You get negative here and positive here, so it is negative, so that would be concave down. And over here it's going to be concave up. So concave up, let's see, negative infinity all the way to 0. And then starting again at 2 and going to infinity. And concave down. Only between these 2 points right here where the second derivative didn't exist and where it equaled 0. So that's going to be from 0 to 2. So actual points of inflection. 0 comma something and 2 comma something. And we could plug those in. What would it be for 0? Look at the original function. It's going to be 0. And if you plug in a 2, let's see, that's going to be the cube root of 2 times 6. So 6 cube root of 2. Is that all right? So it takes up a whole paper to do this problem. And let's draw our rough sketch. It's going to look something like this. Come down here, go like this, and then kind of, whoops, got to make that, yeah, we've got to make that concave up. Okay, so something like this. Here's our minimum. What was our minimum? -1, -3. Point of inflection at 0, 0, and this point right here would be 2 comma 6 radical 2. That's what we're expecting to see. Okay, we'll type this into the calculator and see if that works out. So let me clear that off. Oops. Go up here. So x raised to the 1 divided by 3 multiplied by x plus 4. And I'll hit zoom 6 so we can get a big picture of this. That looks good so far. Turns around, goes like that. Does that look like what we have here? Okay. And it does look like it's concave up. It does look like it curves around like this just a little bit. We could maybe zoom into different parts, change the window so we could see that curvature to the graph and stuff like that. Okay. Tough problem though. Okay. Let's look at one that's even more interesting. Okay, now I would say that this problem is a little bit, just slightly. I mean, I certainly wouldn't give you a quiz on this right now, but again, the ideas here are pretty darn good. As ugly as this looks, this is actually going to be hopefully relatively easy if we're careful and make sure we find the derivative the right way. Again, it's not going to be finding the derivative. It's going to be simplifying, setting equal to 0, and stuff like that. So I'm going to find the first derivative. Can't be algebraically simplified. So it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Now, we're not going to have time to finish this whole thing, but we can at least get it set up and get it to a point where you could finish it by doing the algebra. I want you to take a good look at this. This is a rational expression. Normally, rational expressions have domain issues. We've got division in this. Are there any problems plugging real numbers into this? Nope, because when you plug in a number, it's going to get squared, then you're going to add something to it. So the very smallest the denominator gets is 4 if you plug in a 0. So this will exist for all real numbers. This doesn't have any holes or vertical asymptotes or anything. Remember that from 1050? Okay, so I've just found the derivative, and now we want to make it useful. So what I notice is there's, well, let's see. It'd be nice if those were in common, right? Okay, but they're not. I do have a 2x that I can take out, so that might make things a little bit easier. So let's take out a 2x and look at what we're left with. X squared plus 4, and then make sure you're careful, especially with the negative. That's a minus x squared and a minus minus 4, so that's a plus 4, all over x squared plus 4 quantity squared. X squareds go away. I've got a positive 8, so this is 16x over x squared plus 4 quantity squared. When does it equal 0, and when does it not exist? Never. When does it equal 0? When x equals 0. Okay? So there's our critical value. We're going to put that on our sign line. And it's there because the derivative equals 0. So it's just going to change, hopefully change sign on either side there. Okay? All right. Any questions? Okay. You should be able to finish that. Relatively easy. At least figuring out increasing, decreasing, maxes and mins and stuff. In fact, this one's really easy because what do you notice about the denominator? Like we said a second ago. Always positive. The only thing that's going to change the sign of the first derivative is the numerator. Okay? So that should be relatively easy. Let's find the second derivative because this is where it gets just a little bit tricky. If I find the second derivative, I'm going to take this expression right here, that simplified form, 16x over x squared plus 4, quantity squared, and I want to find the derivative. I am stuck using the quotient rule, so I'm going to have the bottom times the derivative of the top minus the top times the derivative of the bottom. Now careful here, the bottom is a chain. 2 x squared plus 4 times 2x, right? All over the bottom squared. X squared plus 4. It's already squared. I square it again. This is going to be to the 4th, right? Okay, take a good look at this. How many terms do I have on the top? Just 2. And notice that this has a factor of x plus 4. It actually has x squared plus 4. It actually has 2 of them. And this has a factor of x squared plus 4. So let's take out an x squared plus 4. Again, I'm not doing any calculus. I'm just doing a bunch of algebra. We could take out a 16. You want to take out a 16? Let's take out a 16. Okay? So this is going to be x squared plus 4 minus, I took out the 16, I took that out. So I'm left with, let's see, what have I got here? 4x squared? Is that right? All over x squared plus 4 quantity to the fourth. I'm going to cancel this with one of those, so that's going to be to the third. And then I'm going to clean this up just a little bit. That's a 16. This is a minus 3x squared plus 4 all over x squared plus 4 raised to the third. With me there? Okay. We want to know where this equals 0 and where it does not exist. There's nowhere where it doesn't exist. I want to know where this equals 0 then. So when does negative 3x squared plus 4 equal 0? When 4 equals 3x squared. When x squared equals 4 over 3. Or when x is equal to plus or minus 2 over radical 3. Possible locations, I'll put locales of points of inflection. Okay? So if we kept track of the second derivative, 2 over radical 3 would be on there because the second derivative is 0 there, and negative 2 over radical 3 would be on there because the second derivative is 0. Okay? Which, a little more algebra. If I take a negative out, and let's see, and a 3 out, I'd be left with x squared minus 4 thirds. Which I could write as negative 16 thirds. Let's see, make sure we get this right. That's a difference of squares, minus 2 over radical 3 and 2 over radical 3. And then write the denominator there. I think you could do it that way. Okay? But we've identified all the important parts here. And then you could finish it off. Tough problem, but all those ideas are solid. Okay. Any questions? Okay. Chew on that over the weekend and get 4.3 done. Okay. If you have questions, I'll be around tomorrow. If you want to email me a question or something like that, I'd be happy to entertain those too. All right. Have a great weekend.